All right, so let's see. What did we talk about last time? And why isn't this writing? There we go. So last time we talked about magnetic torque coils, which are a very nice kind of low swap, right? Like low size weight power, um, and cheap way of getting some amount of attitude control. They're very common. They're used on big satellites for so-called momentum dumping to offload angular momentum from your wheels. uh, instead of thrusters, which would be the other way to do that because they don't take propellant. And they're often the only attitude actuators on small sats like CubeSats because they take up very little space and they're kind of easy to do. And then we talked about the classic B dot and B cross detumbling algorithms. Uh, these are these kind of classic controllers that basically try to just zero out your angular momentum because often spacecraft will come out. Particularly small sats will very frequently come out with what they call a high tip-off rate. So they come out kind of tumbling out of the deployers for various reasons. And these controllers are really just designed to slow the tumble down and get them close to kind of zero net rotation. And they're really simple and really easy to implement in like a couple lines of code, right? So we talked about that last time. Any questions about that stuff? It's been a while. I'm cool with that. Okay, so today we're gonna sort of where we're headed is kind of we're going to start getting into um, sort of more gyrostat style spacecraft. So in particular, reaction wheels and things like that. And today we're going to sort of ease into that story in a little bit of a kind of like chronological historical way. We're kind of going roughly historical with this. We started with the gravity gradient stuff, which was one of the earliest ideas for attitude stabilization. The next thing we're going to talk about are um, today what are called dual spin or momentum bias spacecraft, which chronologically were kind of the next evolution from gravity gradient and spin stabilization. So these started to have kind of spinning things. They started to kind of be gyrostats with either rotating parts of the spacecraft or internal wheels. And I can't spell. And then, sort of depending on how far we get through that story, we'll talk maybe a bit about flat spin recovery, which is a fun problem with these, particularly for these kind of spacecraft. So it's the problem of if something goes wrong with your controller and the spacecraft, like we talked about before, right? In the presence of any kind of energy dissipation, things will tend to go into a flat spin. And for these kind of momentum bias and dual spin spacecraft, if there's some kind of failure of the actuator, that's what's going to happen. So they end up in a flat spin. So this is a very classic problem of how do you get them out of the flat spin back into their nominal kind of pointing configuration. So we'll talk a bit about that with some show and tell. And then hopefully by the end of the day, we'll start talking about reaction wheel arrays and how those look, and in particular, talk about actuator Jacobians for these things. And that's probably going to be it for today. And then we'll kind of um, from there get into sort of pointing controllers when you have wheels and thrusters and things like that. All right, so any questions about anything? Feeling good? Okay, here we go. So here's kind of this dual spin slash momentum bias idea. So dual spin spacecraft were kind of invented in the early 60s, and they were kind of the next evolution from spinning satellites. The idea was that spinning is cool because it's passively stable, but it's annoying because the whole satellite's spinning. So you can't, for example, separately point solar arrays at the sun and antennas at targets on the ground and or cameras at targets on the ground. So the idea was you would take your spinning spacecraft, which was the other issue with spinning satellites is that, like we saw, they need to spin about the maximum moment of inertia, which is kind of pancake style. And pancakes don't fit into rocket fairings very well. Rocket fairings tend to be long and skinny. So long, skinny rocket fairings tend to favor long, skinny spacecraft, which would be minor axis spinners, which are nominally unstable. So this is kind of a way around both of those issues. So the idea is you have this kind of cylindrical bus that spins, and then you have sort of a giant slip ring. So this is like big bearing with like cable pass-throughs that can go through. So you can have wiring go through this. And then you have a sort of despun platform. So you have another chunk of spacecraft up here that is spinning, that's attached by some bearings and a motor that then has kind of antennas and cameras and whatever on it. And this was kind of pioneered by Tony Irillo at Hughes. He kind of figured out how to stable that. He modeled these things and figured out how to make them stable in ways that kind of generalize the simple minor major axis stuff. So these things, even though they're long and skinny, if you do it right, you can make these things stable. And then there's just a motor kind of despinning that platform with the antennas and stuff on it. Okay, so that's called a dual spin spacecraft. And then kind of the next evolution from there is the momentum bias design. This starts to look more like a modern spacecraft. So here we've got a bus that will just kind of models a box. And it might have, solar arrays on it, all the usual things. And then what you do here is you're trying to really have the same kind of passive stability. But what you're doing instead is you're putting all the momentum in a wheel that's inside the bus. Oops. So this thing, the whole spacecraft is not spinning. And all the momentum is put into this like internal rotor. So in both cases, these actually, in terms of pointing accuracy, these can do quite good inertial pointing. If designed well and implemented well, right, modulo sensors and all this kind of stuff, these designs can achieve sub-degree like inertial pointing. So quite good. So why wouldn't we like this kind of thing? So let's say you can point it within a degree. Like, what's the big disadvantage of a design like this versus a modern like three-axis stabilized thing with an array of wheels? Anyone have any thoughts on that? So they're really stable because they have a big fat angular momentum vector. What about slewing? What does it look like if I want to change the attitude? So they have very stable inertial pointing that can be quite good. But if you want to slew this thing, you end up having to use a ton of torque to move that big angular momentum vector around. So they're very slow. They're not agile. And so that's kind of the main disadvantage of these things and why kind of modern designs have um, okay, but they have this nice passive physics that basically keeps them inertially pointed without active feedback control. So roughly what happened is like in the pre-computer era, these kind of designs dominated because they relied on passive physics and didn't need an active feedback controller. And then in the 80s, when we started to have like better, cheaper embedded compute, and it became possible to run real-time feedback controllers online, that's when three-axis, with feedback controllers kind of became more prominent. We'll talk about that next. Okay, so how about the model of these guys? So these things mathematically actually are identical. They're both gyrostats with like a big fat spinning part and a despin part. So in terms of modeling, they're identical, which is kind of interesting. So as a refresher, it's kind of both end up looking like this. We have our so-called gyrostat equation, and I'll write the whole thing out because we haven't seen it in a little bit. So that's the body inertia, body angular acceleration. It's the rotor torque, rho dot, and then we've got kind of and everything's in the body frame. I'll be extra careful this one time since we're a little rusty. And then this is the external torque over here. So in a lot of cases, these sort of dual spin or momentum bias spacecraft, you basically point it where you want it to point forever, presumably, more or less. And then if you want to move it around, you have to apply external torque with either thrusters or magnetic torque coils to kind of slowly nudge that angular momentum vector around to get it to point somewhere else, which takes a long time and is slow, generally. Okay, questions about this? So far, so good. Okay, so what we're going to do real quick is just look at like what the stability of this looks like and kind of revisit some of those ideas again, because I think it's good for you. So the general recipe is same kind of stuff we've done. We're going to like linearize this thing and look at eigenvalues, and it's pretty easy in this case. So we're going to assume that like we're going to assume a coordinate system where the rotor axis is along the sort of B3 direction. And then we'll assume that we're in some diagonal sort of principal axes coordinates to make the math easy. So we've got an inertia that looks kind of like this. So we'll call it Jx, Jy, and then Js for spin axis, I guess. And then we're going to assume we're nominally spinning about that third axis. I'm going to call this omega naught. So if we kind of write out the Euler equations for this guy, like we've seen a bunch before, we can write these in components. It's just me kind of substituting a bunch of stuff in and simplifying stuff down. And remember, I've only got one row here, right? There's one big wheel or one kind of spinny thing. I don't have, so that's not a vector anymore. That row is just a scalar. I'm assuming no external torques. So we get stuff that looks like this. And then the spin axis is really easy. Okay, so this is kind of our three in components, the three gyrostat equations. So if I look at this real quick, very kind of obviously, the spin axis equation is kind of trivial and decouples from the other two. And that one, we basically have full control authority over because that rho dot thing I get to pick. It's the torque applied to the rotor or the torque applied between the D-spun platform and the spinning body. So that one, we're just going to assume that we have a controller running, like, do PD control or whatever to keep it spinning the way you want. And then we only have to worry about two equations. So the spin axis dynamics are decoupled. And we're going to assume that we've got some controller doing something. Right. So, there's going to be bearing friction and stuff like that. So ultimately we want that thing to be not spinning about that axis. So we just run a very, very simple controller on that one motor to basically zero out that omega dot Z. Right? Okay, so now we're going to look at the other 2 degrees of freedom, the first two, which we'll call the transverse dynamics. And this is really, really easy. And we get kind of our classic linear system-y thing with a little bit of massaging. Okay. Okay, so this looks like x dot equals ax. We've seen a bunch now, right? And this is a nice, easy little kind of like 2 by 2 matrix. I'm going to call this, we're going to just write this as like A and B, two scalars in here. And it's a really nice little simple kind of matrix that looks like this. And um, this thing has, ultimately what we want to do here is make this thing be a simple harmonic oscillator. We want it to be, that's the best we can do, assuming there's no damping, which I didn't model damper in here. So the best I can do is marginal stability, which is like simple harmonic oscillator stuff, which means this thing has pure imaginary eigenvalues. So that's what we're going to look for. And for a 2 by 2 matrix, the eigenvalues are really easy to calculate. You can kind of do it in closed form. And here, what it's going to look like is, right, so this is the kind of definition of eigenvalues. And if I kind of stare at this for a second, these are going to be plus minus square root of A times B. So again, if I have, so there's kind of two things that can happen here. I can have lambda be a positive negative real pair, which is bad because the positive eigenvalue is unstable, it means I blow up. Or if A times B is negative, this is going to be a pure imaginary complex conjugate pair, which is an oscillator, right? So we want A times B to be negative. And just from that condition, I get like a couple of, just kind of two options. I can have rho bigger than this and bigger than this. And if I just kind of stare up here, what I'm trying to do is get like one of those to be positive and one to be negative. And literally all that's saying is if I jack rho up, so if this scalar is bigger than like these two terms, then this one's going to be negative, this one's going to be positive, life is good. And I get a simple harmonic oscillator, or I can go the other way and have it be strictly smaller. Sort of an or in here. So these are the options. So this like basically will, assuming things are nice and I spin everything up and I set that rotor momentum to kind of satisfy these conditions, I get a nice, stable, simple harmonic oscillator thing. There's some slightly more complicated details around if you have damping and stuff, but that requires some fancier analysis that I don't think we need. Okay, so now the question is, so this is if everything's perfect and we've linearized and assumed small angles and stuff like that. What happens, like how do I get myself there? And or what do I do if something bad happens and my like controller fails and I end up way outside the sort of local stability region of this thing staring, right? So this gets into a really fun problem that's a kind of a classic problem that dates back to this era when dual spin spacecraft were the state of the art. It still comes up once in a while and it's still cool, I think. And I've worked on this a bit, so we'll do some show and tell. But we're going to talk a bit about like how to deal with that. So this problem is called flat spin recovery. Okay, so the idea is if I have a spacecraft like this, if anything goes wrong, I can end up in kind of an undesired major axis spin, because that's just where everything will settle down eventually. So if my controller fails, my actuator fails, this is where I'm going to end up. And basically, this is all about like, we need some kind of control strategy for recovering from that. And yeah, this is kind of especially, it's a general thing, but especially for like for the dual spin case, this is kind of a classic thing. Because in that case, it is a minor axis. If you lose the actuator, it becomes a minor axis spinner, and there's internal damping, so it will go into a flat spin if something goes wrong. Okay, so um, let's see if we can kind of intuit how to do this. So, do we remember kind of the energy arguments around like the major versus minor axis spin stuff? So, which one's the an energy min? Major axis, right? That flat spin. That's why this thing will go into a flat spin passively. Okay, so the minor axis is an energy max. It's the thing with it's the state, the maximum energy state. So a really easy way to like derive a controller that can do this is to think about energy. So I want a control law that will essentially pump energy into the system, right? And if I do that, basically like based on some very simple arguments, if I just try to pump energy into the system and increase the kinetic energy, it will end up eventually converging to a minor axis spin. Does that make sense? So let's write that down and check it out. So this is the thing we want is a maximum energy state. So all we have to do is pump energy in. With our controller. All right, so let's figure out how to do that. So kinetic energy is what here? Need a little help. Maybe wait for this. Well, it's omega because we're spinning, and this is omega transpose j omega, right? Done this before. Okay, so now what I want to do is take the time derivative of this. So I do that. I want t dot, and this is just chain rule. So I'm going to get um, omega transpose j omega dot. Cool. So it's dt d omega times d omega dt. dt d omega is j omega, or omega transpose j, times omega dot. So that's that. And so now what I'm going to do is I'm going to plug in the dynamics, the gyrostat dynamics for the omega dot. So that looks like the following. So I have, we know what these look like, right? So these are our nice gyrostat dynamics. I'm going to solve these for omega dot. Just move everything over. And now I'm going to plug this expression for omega dot in there. So I'm going to have that minus sign out front, omega transpose J. And then I just plug the whole thing in. I get J inverse, bunch of stuff. So rho dot plus omega cross J omega plus rho minus tau. And now a bunch of nice cancellation-y things happen. So very obviously this thing, J times J inverse is an identity. So this goes away. And then some other kind of slick things happen. Okay, so if I look at this term, so this is gone. So I have omega transpose rho dot. I have omega transpose omega cross stuff, and I have omega transpose tau, right? Okay, so we can think about some geometry, some linear algebra real quick. Can anyone tell me what omega transpose times omega cross stuff is going to be? Okay. So let's think about some cross products and dot products for a sec. So this is omega dot omega cross stuff, right? If I do omega cross stuff, the answer to this guy, this omega cross thing, has to be perpendicular to omega, right? So I have omega cross stuff, which is automatically perpendicular to omega. If I then take a dot product again with omega, it's got to be zero. Because by definition, omega cross anything is orthogonal to omega. So then the dot product's got to be zero. Yeah, everyone follow? So this term also drops out and goes to zero. So this got really nice all of a sudden. And this whole thing ends up being minus omega transpose rho dot plus omega transpose tau. Okay. So what this is basically saying is this is the derivative of the kinetic energy with respect to rotor torque and external torque. So this is like my rotor stuff, and this is like thrusters or torquers or whatever. Pick your favorite actuator, and then literally all I'm trying to do is drive T dot up. So that's it. So I can basically make up any control law I want for rho dot and or tau that's going to drive this quantity, this T dot quantity positive, and that'll pump energy into the system. And there's many choices here. We kind of looked at some stuff like this last time. But if you want something maybe kind of super simple, a reasonable choice here would be to set rho dot equal to minus some constant or gain times omega. So if I plug this in here, I'm going to get plus k omega squared, basically, which is going to be always non-negative, always positive, basically, and that's going to drive the kinetic energy up. Or if I want to use thrusters, I would get like tau equal to k omega, right? Because that one doesn't have a minus sign, so this is going to, again, give me something that's like proportional to omega squared. That's always going to pump energy in. Make sense? And then this is some kind of gain. So this is like simplest linear control law for this. Let's see. Any questions about this? Does anyone recognize the argument that I just made to do this as something you've seen before or heard of before, or we've talked about before, vaguely? So I didn't call it that, and maybe it was like slightly in disguise. This is a Lyapunov proof, and this is a Lyapunov-based controller. So the Lyapunov function here is the kinetic energy. Usually with Lyapunov stuff, you try to design a Lyapunov function that's zero at the point you want to get to, and then you minimize it and drive it down. So if I stick a minus sign on this, this doesn't obey the sign conventions and some of that stuff, and it's more intuitive in physics-based, but this is a Lyapunov stability proof that this controller is stabilizing and that it will drive us to the desired equilibrium point. We've talked about this stuff vaguely. Has anyone done this kind of thing before? Know what I'm talking about? No? Okay. We sort of talked about it a bit before, but this is why, we didn't do a lot of this in this class, but hopefully the physics argument made sense. Yeah? Sort of, kind of, maybe. All right. Let's see. We'll say a few more things about this. So yeah, you can do this with kind of rotors, wheels, or magnetorquers or thrusters. Fun fact, you can also use the same control law as a nutation damper. We talked about the Kane damper and this kind of like passive kind of stuff. It turns out this basically looks like derivative control, right? If I look at the expression for this control law, like it's a minus k omega. So it looks like a minus damping constant times a velocity thing. So this looks actually basically exactly the same as a Kane damper, but now I'm implementing it with a controller and an actuator instead of a physical piece of hardware, which is kind of interesting. And it turns out you can actually typically get better performance out of something like this than a physical damper in terms of sort of size, weight, and cost and stuff like this. Like I can use a very small wheel with a really simple control law and get more damping performance than if I built a physical damper. Oops. But then you have to worry about the actuator dying and other things. So I guess there's maybe slightly higher risk than a hardware damper. What else to say about this? Oh yeah, okay, here's a fun thing. Fun anecdote. Okay, so if I think about what this controller is going to do, and I remember like my momentum sphere idea. Um, so I have this spinning thing. With this controller, I can end up spinning this way or this way. It doesn't determine which way the spin axis will point, only that I get into a minor axis spin. So I can't do anything to control the polarity of the spin. And sometimes that's a problem, right? Because it's totally symmetric and it doesn't care. All it's doing is pumping in kinetic energy, and this have the same kinetic energy. So it can't do anything about that, which is kind of interesting. At least this is which is the classic kind of method. Basically, this thing has two equilibrium points. If you think about the momentum sphere and the kind of the stuff we did before, there's kind of minor axis spins on, say, North Pole and South Pole, and they have the same energy. So which one you end up in is completely random based on your initial conditions that you start out with here. Okay, and now we get to have show and tell because it's fun. All right, so check this out. So this is stuff I did in grad school and shortly afterward. This is a crazy thing that I spent a bunch of time on my PhD called KickSat, where we built these tiny little 4-gram printed circuit board satellites and then packed them into a 3U CubeSat and then flung them out in space like this. And the goal was to get these things to come out, say, little solar panels, and they're pancakes, right? So we wanted to spin them up and then fling them out so that the little solar panels were, so they were spin stabilized and they were major axis spinners. And their solar cells were pointed at the sun. That was the goal. And so to get that to happen, like these things don't have any control. We were going to use the CubeSat, which had wheels in it. We were going to point this face of the CubeSat at the sun, spin the whole CubeSat up about its minor axis, and then fling these out. And so if we did that right, by relying on the control system on the CubeSat sort of mothership, we would fling these guys all out so that they were all major axis sun pointers when they were deployed. Make sense? Okay, so we did this kind of flat spin stuff. And that's kind of the cartoon picture. We want to, yeah, point all the solar panels at the sun. This thing has little reaction wheels that were little motors. And yeah, trying to get this minor axis spin to happen. But we actually cared which face was at the pointed at the sun. So this idea of this like possible polarity flip that can happen, we just talked about with the classical controller, was no good for us because we needed one specific face of this guy towards the sun to make sure the solar cells were pointed at the sun. Okay, so this is kind of stuff we've done so far. and this is the momentum sphere picture, right? So these are the equilibria. We've kind of looked at this kind of thing. So this is the unstable one, right? And this is kind of the separatrices. And then these are kind of the stable. This is like major axis, minor axis. And then there's kind of north and south poles that are the same, right? And these are kind of the gyrostat dynamics that we just wrote down. And here I'm just like rewriting them in terms of angular momentum instead of omega for convenience. This is like cartoon Lyapunov stability. So the idea is we have a Lyapunov function V that's a bowl. Usually it's some energy-ish function. And then we try to make sure that the system trajectories with the controller turned on always go downhill in the bowl. So V dot is always negative. This is exactly the same argument I just made with T instead of V and with the signs flipped, right? So we had a T and we were trying to make T dot positive with our controller. So it's the same idea, just flip things around. So here's the one we just did, which is this kind of quadratic Lyapunov function. And we just try to drive, this is rewritten in terms of angular momentum, but it's just trying to drive the energy up, right? So this is just the energy we wrote down with a minus sign in front of it so that it's trying to drive it to zero instead of, and then this is just this is a constant offset such that it has a minimum at zero. So this is just me massaging the argument we just made into like official Lyapunov proof where the minimum's at zero and we're minimizing instead of maximizing. And this is the picture on the momentum sphere that you get. So the minima are at the north and south poles. These are maxima. And it kind of looks like this, but this is annoying because it has this symmetry and I can end up in either north or south pole, which is not what I want. So we're going to try to fix this and avoid this annoying kind of sort of possibility of ending up upside down. So here's another thing you might think to do. Like an obvious thing to do would be to write down a linear function that has only a single minimum at the North Pole and has like a max at the South Pole. So this thing would get the job done, right? It would force me to the North Pole and not the South Pole. The problem with this is I can't guarantee that this is always negative because I have very weak little actuators and I'm trying to just nudge it a tiny bit at a time. So really what I need is for like the uncontrolled. So if I imagine the uncontrolled system trajectories, I'm kind of spinning around and I have some like orbits on this thing. The V function evaluated along uncontrolled system trajectories is doing a bunch of crazy stuff. It's like oscillating all over the place and I can't get V dot to be negative all the time. So the trick here is I'm going to take this function and I'm going to average it along solutions of the like natural open loop dynamics so that if I don't do anything with the controller, V dot's zero here. And so then like it kind of sets me up to be able to nudge it a tiny bit. So this is what happens if I take that linear function and average it along open loop trajectories of the natural dynamics. Interestingly, right, I get the similar kind of behavior where this is a max and this is a min, but now around the major axes where I have these periodic orbits, basically those average out to like constants. And so this whole region becomes sort of just a constant. So that this is now a problem because it won't do anything in these regions. There's no sort of hill climbing or descending happening. It's flat in those regions. So then what I do is just add those together. So I take that weirdo averaged linear thing and I add it to the quadratic thing that I had before. And now what that gets me is kind of the best of both. So the quadratic thing pushes me out of the major axis spins, and the linear term makes sure I head towards the North Pole and not the South Pole. And then there's a whole bunch of math details about how to actually calculate the controller, which are kind of irrelevant here. This is all kind of like how to do that periodic averaging trick. Here's what you end up with in the end. And this is kind of, we used the kind of switchy flavored thing instead of a linear thing. And we had this conversation last time, right? We use a tanh for a couple of reasons that are, it has some niceness properties. You get two tuning parameters. You can set the the sort of saturation, and you can set this slope with this alpha, which is kind of convenient. And then here's what it looks like. So here's an example of it starting over here with like a flat spin, and it kind of winds its way out gradually and then crosses the intermediate separatrix and then heads towards the North Pole. And then here's kind of the, I guess here's what the inputs look like. Fun. That sort of smooth saturation gets you this kind of behavior where it's doing bang bang things when the errors are big. And then when it gets close, it looks like a linear controller over here, which is what you want. So it doesn't thrash. And then here's the kind of really fun one that doesn't happen with the nominal controller that we just wrote down. This gets you this kind of spin inversion behavior where if I'm spinning the wrong way, it'll actually wind me out and then flip and wind me back towards the North Pole. So it gets you like kind of all the things you want. Okay, and I don't know, that's what that looks like. Kind of cool. So you can fix the classic with some tricks. That's what Lyapunov stability looks like. I don't know. Kind of fun. Thoughts, questions? No. Okay. All right. So what's next? Oh yeah, there's a fun little like extra nugget from that. Um, all right, so I guess the note here is you can fix this with a more complicated Lyapunov function, which is what I just showed you. But there's still one quirk, which is that, which I think is a fun thing that you should know about. Um, so I kind of created this, I shaped the dynamics so that it will flip if you're sort of pointed the wrong way. What happens if you're exactly on the South Pole, though? Yeah, why? Sort of two questions. The first is why? Like you intuited the answer clearly. So can you, and then the second question is that a problem in real life? But why not?
Don't know the math behind it.
But yeah, let's hear the intuition.
But my thought is
Like you intuited the right answer, but yeah.
if you're stuck exactly at the South Pole, uh, my guess is that the system isn't stable enough to maintain it there. It's gonna naturally wobble at some point, and then the controller can kick in.
Exactly. So the South Pole is another equilibrium of the system, and it turns out there's no way around that ever. Um, but it's an unstable equilibrium. So in the presence of any kind of noise, you're going to get knocked off a little bit, and then it's unstable. So exponentially, it's gonna head out of there away from. So it's a mathematical quirk that's annoying, but it's not actually a practical problem because as soon as you have any noise, it's a set of measure zero. You're going to get knocked off of it and go away. Okay, so to formalize that slightly, and to also name drop a hilarious name for a mathematical thing, there's this classic result that says uh, it's called the Harry Ball theorem, and it says that has anyone heard of this before? It's a fun Wikipedia. Okay, so the gist is you can't have a globally non-singular vector field on a sphere. And so the intuitive picture of this is I draw a circle and I try to draw a vector field, i.e., a bunch of arrows on the circle that are all like, say, I want to stabilize the North Pole. I draw a bunch of arrows pointing towards the North Pole. I have to have uh, another singular point, another equilibrium, another point where the vector field goes to zero somewhere else on the circle. So if I naturally point all the arrows up, there's going to be somewhere, like i.e. the South Pole now, where those arrows are all pointing out, but they have to be zero somewhere else. And I can't get rid of that. Um, And there's a couple ways around this. One argument that I just made is you can like resort to noise and say, oh yeah, there's noise and that thing's unstable, so it's not really a problem. The other way to get around this is it turns out that theorem applies only to time invariant vector fields. So if it's a constant control law, constant vector field, if you make it time varying, you can basically wiggle that point around in a time varying way that also kind of gets rid of the issue. But again, if there's noise, it's not an issue, right? Um, So this looks something like if I imagine, let's go to the like simplified like 1D case. I have my equilibrium point I want up here. I guess let's make that green. What the hell? And then I try to draw like a bunch of arrows pointing to this. It's kind of what we just did more or less, but like a fancier 3D version. I basically can't get around there being another fixed point over here. And yeah, uh, if you want to Wikipedia this idea, it's called the hairy ball theorem. The exact statement of this is you can't comb a hairy ball flat. That's the classic quote. I didn't make it up. It's like thinking about like a koosh ball or something like this, right? And you try to like, yeah, whatever. Okay, we're done with that. Okay, let's see. It's pretty good. Any thoughts, questions on any of that stuff? Not a fun problem. I went really far down the rabbit hole on that one for a long time at grad school. That kicksat thing. It was a lot of fun. Uh, okay, so I think we're done with this kind of dual spin momentum bias stuff. And now I want to talk more about like how to think about classic, standard reaction wheels and thrusters that we're used to seeing on modern spacecraft and kind of ease our way into tracking controllers and all that stuff. So kind of the first topic to talk about there are so-called actuator Jacobians and kind of what actuator arrays look like on typical spacecraft. So the idea here is so far, we've written our dynamics sort of generically in terms of rhos and taus, right? So we're just assuming there's some momentum, internal momentum vector from some set of wheels somehow, and some external torque vector from some kind of, thrusters, whatever, environmental torque somehow. So we've got, rho and tau. Here's our gyrostat thing again. It'll be a little bit looser with I won't write all the frames on here. So hopefully we remember what we're doing now. Right. So that's kind of the full-on gyrostat thing with the internal momentum from rotors and the external torques. And the kind of thing to talk about now is that now we're going to talk about actual actuators. So it's thrusters, reaction wheels, CMGs. We'll probably get to in a little bit. And so we need mappings from the actual U's, the actual actuator commands into rho and tau. So actuator commands being reaction wheel torques, thruster thrusts, I guess, forces, etc., and the rho and the tau. Okay, so we'll talk about thrusters first. And so the gist here is like you're never actually going to have, three of these things that perfectly align with body axes. Typically you have more than the minimum number for redundancy. So for thrusters, we'll write sort of tau sub T for thruster, I guess, in the body frame. And we're going to sort of have a sum over number of thrusters. And really what we're just going to do is it's R cross F is torque, right? So we'll have an R for each thruster crossed with the F for that thruster. And this R is the thruster position relative to the spacecraft center of mass. And then I can like slightly rewrite this, or kind of as that same R crossed with what I'll call A, which is going to be the thruster axis unit vector. So we've got the offset from the center of mass where that thrust is applied. Then we've got the direction the thruster is actually pointed, right? And so the cross product of those two things gives me the torque from the thruster. And then this is times the actual U, which would be the sort of thruster command. So this one is thruster axis unit vector. And then this is sort of thrust command, which would actually have units of force here. And if you wanted to, if you have different units on that, you can wrap this whatever constant you want to rescale the units into this Jacobian. Okay, so that's like if I add up all the thrusters, I have a little input, thrust like force for each one. And then from a bunch of geometry calculations here, I get the torque for each individual thruster. I can sort of summarize that whole expression into a nice little matrix. It gives me this torque. It's going to look like the following. So I'm going to have R1 cross A1, then like R2 cross A2, dot, 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 for all my thrusters, and then Rn cross An. So that's kind of this term for each thruster. And I stack them in a matrix, and then I've got my vector over here of all the U's. And this matrix, so input Jacobian things are always B, like in the linear systems case, we're AX plus BU. So we usually use the letter B for this kind of input Jacobian mapping that maps U's into kind of forces or whatever. So we'll call that B sub T for thruster input Jacobian. Cool. Any questions? Cool. So here, this U is the force applied by each thruster. And then if I map it through this Jacobian, it's going to be the torque applied by the total torque applied by all of the thrusters added together. Right? Okay. So that's thrusters. Now we can do kind of a similar thing for reaction wheels. Okay, so the kind of intro story here is the bare minimum you would need to have full actuation of all your degrees of freedom is 3 wheels. How many thrusters do you need to have full actuation? That's a fun question. It's more than 3, it turns out, because you can't pull with a thruster. It can only push as a, well, that's a different input then, right? Then you'd have to gimbal the thruster. So yeah, I mean, you're not wrong about that if I had, but that's another sort of, so if I have a fixed array of thrusters, which is kind of the normal thing, it's more than 3. Bonus question. Okay, so you need at least three of these guys. So you know how to figure that out, by the way. So the sort of being fully actuated is equivalent to this B matrix having full rank. So this thing has to have rank 3 for me to be able to produce any output torque. If I look at each one of these little guys, what's the rank of one of these blocks? Like, what are the blocks? Yeah, I don't know. I'll leave this for you to think about. All right, so usually spacecraft have 4 wheels at least. Um, and yeah, 4 is kind of standard. Some have more, like Hubble, for instance, I think has 6 or 8. So it's often like if you really, really care about pointing, you'll have more, but 4 is pretty standard. And there's kind of interestingly, some standard configurations for this. So if I gave you 4 wheels instead of 3, how would you arrange them? Thoughts? What does that mean?
I don't know how to describe it. Like,
So if I had 3, I'd probably do kind of a roll pitch yaw kind of thing, put them sort of along orthogonal axes, probably, right? So if I had a fourth one, what do I do?
the picture has, you have a cube,
Yeah.
each one of them pointing to some.
So sort of like a tetrahedron kind of thing. Yeah. So that's a very reasonable choice. Um, so the gist is you want to take the last one and array them in such a way that like so obviously you don't want to double up. What you want to do is have that fourth one have some component along all of the other axes so that you're single fault tolerant. So basically, if I lose one of these, I still span R3 with the remaining ones, no matter which one fails, right? So that's kind of the most basic thing is you want to make sure that like no pair are linearly dependent, such that I'm always single fault tolerant. Um, But beyond that, there's actually no consensus. They end up with slightly different sort of what you'd call, and so in the nominal case, these different configurations will result in a slightly different torque envelope, so like slightly different maximum actuator capability envelope. They're all single fault tolerant, and there's a few common choices. Um, so the first one, which is frankly the dumbest, is the so-called JPL configuration. This one is sort of maintains the first 3 in sort of the classic 90-degree kind of orthogonal thing, and then adds the fourth one, sort of just splitting the difference between those, which is so it's doing this, which gives you single fault tolerance, but in terms of control capability sort of envelope in the nominal case where all of them work, it's kind of the worst, or doesn't necessarily do the best. Another common one is a pyramid configuration where they're kind of, you can imagine sort of at the 4 corners of a pyramid pointing up to like the point at the top of the pyramid. So let's see if I can draw this. Something like this, vaguely. Hopefully that conveys the general idea. And then the last one is kind of, I think the one you were getting at, which is kind of the tetrahedron sort of vibe. So you've got like three of them sort of vaguely pointing, up and in, and then one kind of, I don't know, not the best at drawing these. That looks very, very similar to the previous thing. So maybe we should try to, I don't know, or the pyramid. So these ones it's kind of four arranged in a square, the vectors kind of pointing up towards the top. The tetrahedron is like, I don't know. You can imagine what a tetrahedron looks like. You can Wikipedia the picture, but yeah, it's kind of one of these. You get the idea. That's a bad drawing. Should get some pictures for this. Okay, so these are kind of all possible choices. Maybe that's a little bit better. Not great. Okay, so from here, you can set those up however you want, and then you do the same kind of thing. We can derive a wheel Jacobian. So you have something that looks like this. So we have rho, the body frame, and it's just the wheel axis kind of unit vectors for each wheel. So we'll call this A1, A2, ... up to AN for N wheels. And then over here, we've got the individual wheel momenta. So I guess we'll use W's for these, I guess. So this thing we're going to call B sub W for wheel Jacobian. And then these A's are the individual wheel spin axis unit vectors. And then, so this maps individual wheel momentum scalars into total angular momentum rho for the whole satellite. Sure. And then this, right, so typically how this would look is ultimately I control the torque on these things, or some things have built-in controllers, so you do velocity control. But this would sort of look like, so I might have the total torque from the wheels would be like, so if I'm commanding torque, if use torque, I have the same Jacobian that maps applied torque on the wheels into total torque. And then I would have something like, an integrator on these W's to get to from wheel torque to wheel momentum, right? Hopefully that makes sense. It's integrator on torques. Okay. Last thing for the day. So we got some Jacobians for thrusters and wheels. These are both constants that are just, these B's that we just wrote down are constants that are fixed based on the spacecraft design, right? So you choose an array of actuators, and then that sets up what this B matrix looks like. We haven't talked about CMGs. Those are trickier. CMGs, we're familiar with. I think we talked a bit about them early on, but they're wheels that instead of the wheel axis being fixed and you change the wheel speed, most CMGs have a fixed spin speed and you instead gimbal the wheel axis. So what do we think this Jacobian looks like for CMG array? Much trickier. The A's are changing. So CMGs don't have a constant Jacobian. The Jacobian is a function of the gimbal angles, which is tricky and annoying and nonlinear, and they're much harder to deal with. So that's for next time or next week, probably. Okay, so the last thing we'll talk about is, so if I have this kind of situation, let's just talk about wheels, but same thing applies to thrusters. So I've got a Jacobian like this. It's non-square, i.e. I have more inputs than I have torque outputs. And let's say I want some desired torque. So let's say I give you a tau. How do I decide what the U's should be to produce a desired tau? If this thing is, so maybe I'll draw it like cartoony. vector style. So tau is 3D, say. So this is like a 3D thing. And then in general, B is big and fat, and U is, much bigger than tau. So how do if I tell you I want a certain tau applied torque on the spacecraft, how do I back that into a U that I apply to the actual actuators? Thoughts, ideas?
Solve the linear system.
What linear system?
The BU.
Well, I can't solve this linear system because B is not squared.
Like the two inverse.
Yeah, so yes, but this turns out to be a different pseudo inverse than the one we talked about last time. So there's two pseudo inverses, and this is like kind of a different kind. So the one we've talked about before that shows up in least squares, what's the sort of dimensions of B in a least squares problem? In a least squares problem, I have lots of measurements and I'm trying to estimate something that's smaller than the measurements, right? So that's a tall, skinny B or A, right? We call that A, I think. So in that case, I'm overdetermined. I have a tall, skinny matrix. In this case, I'm underdetermined. I have a short, fat matrix. So in the tall, skinny version, that's a least squares problem. That doesn't have an exact solution. And then the best I can do is find a least squares solution to the linear system. Here, it's the opposite problem. This is underdetermined. So I like actually have an infinite number of possible U's that can generate the desired torque. So it's the opposite problem. I can solve this exactly, but there's no unique solution. There's a whole bunch of U's that would generate the desired tau. So I have a different problem than the least squares problem. Annoyingly, I still call it a pseudo inverse, but you actually have to, it's a totally different sort of object that does something differently. So anyone think of like so basically I have to make a choice, right? So there's an infinite number of big U's that can produce a little tau here. How do I pick a particular U out of there then? Like what's a reasonable choice? I have a suggestion. Least energy is excellent. So what's least energy math-wise?
Lowest speed for the wheels and lowest thrust for the thrusters.
Yes, so that's exactly right. How can I write that down as math?
Yeah.
Min of what? Well, use a big vector. So what do I mean then?
Like element, ergo. Mean of the sum of U or something.
So well, they can be positive or negative, at least in this case, in the wheel case, not in the thruster case. So minimum absolute value. So what that'll do, that's an L1 norm. And that will produce actually something that'll produce the maximally sparse solution. So that'll tend to make a bunch of them zero. And like if I had the JPL configuration and I did that, it would basically always zero out this fourth one and always basically use the other three. So it's not quite what you want. Any other ideas? But it's a good instinct. Yeah, so if you minimize U squared, that actually corresponds to the minimum energy solution. And what that'll do is basically evenly distribute the momentum across the array. So that's like either one is correct and either one will get you an answer. But I think generally speaking, the minimum like L1 norm is going to basically always zero one of the wheels out. And probably that's not exactly what you want. So okay, let's write that down. So the way you would do this then is minimize like 1/2 U squared subject to that equation, like tau equals BU being true. Right? Because this, I can always satisfy that. So I'm going to look for the minimum 2 norm, like minimum U squared, minimum energy solution that kind of evenly distributes all that stuff. Okay. Anyone know how I know you guys know. Anybody who isn't in my lab know how to actually solve this problem? So we'll walk through it, I guess. So I'm going to take this, I'm going to enforce the constraint with a Lagrange multiplier and write down this thing called the Lagrangian. So I just take the cost function, U transpose U, and I'm going to add a Lagrange multiplier times the constraint. So I'm going to write the constraint now. So it's Lagrange multiplier times stuff equals 0. So I just move the tau over. So I do this. And then I set the gradient of this thing equal to 0. And I have to set the gradient of with respect to everything equal to 0. So a grad with respect to u and grad with respect to lambda. So if I do that, I'm going to get u plus b transpose lambda for grad with respect to u of this guy. So like u squared with a 1/2. And this ends up being, this u goes away. Yeah, b transpose lambda. And then I get, if I take the gradient with respect to lambda, I get just the constraint back again. So I get these pair of equations. There's a nice little trick to getting a closed form solution of this. I'll just show you because it's fun. Fun fact. You should know about this, I think. So I can solve this thing for u. Obviously, it's sort of trivial. So this guy I can rearrange into u equals minus b transpose lambda. I can then take this and plug it into the second equation. And get minus b transpose lambda minus tau equals 0. I can rearrange that and solve that for, so now this thing is square and invertible. So I can solve that for lambda. And now I plug that lambda back into the first equation, and then I'm done. So the final answer is u equals b transpose b transpose inverse tau. So I don't know. I find it annoying and dumb that this is also called a pseudo inverse. They're both pseudo inverses, but they're sort of different things that do different things. Like the one we saw before is a least squares solution to an overdetermined system. This is a minimum norm solution to an underdetermined system. So they're like different things, and they have a different expression. They're different things. But anyway, that's what that is. So again, this is like a nice, convenient, simple way to get, if I give you a torque that I want, and you have an array that's like got more actuators than degrees of freedom, this gives you the nice kind of like, roughly speaking, evenly distributed. It'll evenly distribute the torque of the momentum over the array and like overall minimize the individual wheel speeds. Yeah.
Question, for distributing across all of them. If you're running an active standby system, do you want that?
I don't know. Depends. There's no wrong answer here, right? Like this is a reasonable thing to do. You can, optionally turn actuators off. You could, choose a different norm here that would distribute this stuff in a different way. This one is the one that minimizes the sort of like individual wheel speeds the best. And so actually like minimizes the overall energy consumption. Yeah.
Think we can also kind of like the skills that is used in signal processing and imaging, or this is
It shows up all over the place. This is not least squares.
okay.
I mean, to be clear, right? The least squares is the other pseudo inverse that we talked about before. This one is the minimum. So they're two different things. The first least squares is if you have an overdetermined system that doesn't have an exact solution, you minimize the sum of the squares of the errors on the residuals, and that gets you the one we saw before when we did least squares statistical stuff. This one is if I have an underdetermined system, which has like in principle an infinite number of solutions, I need to make some kind of arbitrary choice to like get a unique answer. And so this is saying I want to find the solution vector that has the minimum like 2 norm. Also in a lot of applications that corresponds to the minimum energy solution or something like that. And that's what you get, right? But they come from different problem setups. Like this one has an exact solution. It just has an infinite number of exact solutions, and I have to pick one of those exact solutions. The other one doesn't have an exact solution, and I'm trying to like get as close as I can to a solution by minimizing errors, right? So that's kind of, I don't know, they're sort of like in some sense duals of each other. But yeah, you've almost certainly seen stuff that looks like this, like all over the place. It shows up a lot. It absolutely does show up in signal processing. There's also other fun, weird signal processing things that look kind of like this underdetermined thing, but instead of minimizing the 2 norm, minimize the 1 norm. That turns out to be very, very deep in signal processing. That's called compressed sensing. And like you can beat the Nyquist limit and all this kind of really awesome stuff. Turns out, yeah, if you do this exact thing in signal processing, if you have a situation like this where you're underdetermined, and instead of this 2 norm least squares E thing, you minimize the 1 norm. Remember I said before that will try to zero out as many of the U's as possible. In signal processing, that corresponds to a sparse solution vector, and that's called compressed sensing. It's really cool. And yeah,
Okay, that's really cool. Okay, yeah, there's just something that
I don't know if you've ever heard of this. Yeah, there's lots of fun things. Okay. I think that's all I got. And we're kind of at the MIT 5 minutes early situation. So thanks for coming. See you Thursday.